Okay, let's continue with the multiple choice section. This is question 8. The graph shows the changes in concentration at constant temperature for a chemical system that initially only consisted of nitrogen dioxide. So you can see by looking at the graph that the concentration of nitrogen dioxide, which is NO2, starts somewhere up here, and the concentration of N2O4 is down here, which is close to zero. And you need to determine which of the following statements regarding the system is correct. So let's just quickly have a look at all 4 statements. So the first one, the reaction reaches equilibrium at about 1.4 minutes, and the equilibrium constant is 5.5. Now, it doesn't look like it reaches equilibrium at 1.4. That looks like the point of intersection. So this is when the concentration of the two species are the same, but that doesn't mean it reaches equilibrium. It only really reaches equilibrium at around this point. So statement 1 is wrong, which means that A is not the answer. So this one say that the reaction reaches equilibrium at about 3 minutes, and that's correct. So we're just going to quickly estimate the equilibrium constant. Now, you probably don't have to do that because all of these options have that statement. So the equilibrium constant of 20 must be correct. So I'm just going to assume that this statement itself is correct. So it's all going to be about the other statements. So we look at B. The back reaction rate is at its lowest value once equilibrium has been established, and then you do have some other statements regarding the rate of the forward reaction. So I think a good thing to do in this question, and this is just so that we can quickly revise rate and time graph, is I'm just gonna draw or try to draw. It's gonna be pretty bad because it is quite hard to draw on this. I'm gonna try to do a quick sketch. Already does not start very well. Okay, let me try again. All right, we're gonna do a rate and time graph. Hopefully that's slightly better. Very, very, very rough sketch of the rate and time for the forward and back direction. So let's just look at this. So this is time. I'm just gonna change the color of the pen. I don't know what just happened there. I'm just gonna change so I'm gonna go forward being red. So that this is the forward. And the rate of the forward reaction is gonna start initially. It's gonna be the highest rate because you start with only the reactants for the forward reaction. So the rate of the forward is probably going to start somewhere here, and then it's going to decrease over time, maybe something like that, because as you're making more products, so because you have more forward reaction, that means that the reactant, which is NO2, is used. So rate will decrease. The more you use a reactant, the more the rate will decrease. So this is going to be the forward. Now, if we think about what happened to the back reaction, and I'm not drawing this to scale because I think the scale is slightly off in terms of how much the forward go down, but let's just assume that it only goes down. Okay, I think I may have to redraw that just so that it goes down a little bit more so that it looks more logical. Okay, let's just say that it looks like that. So eventually it becomes a constant, which is when equilibrium is reached. Now, if I use the same process to think about the back reaction, okay, then this is going to be the rate of the back. Now, that's not supposed to be higher, it's supposed to overlap. Let's just try one more time. That's slightly better. Okay, so this is going to be the back reaction, and the rate will increase. Okay, let's try to write that again. Rate of back increases as more N2O4 is made, because if you're making N2O4, you're making the reactant for the back reaction, and that is going to increase the rate. The higher the concentration of the reactant, the higher the reaction rate. Okay, so that will be the rate and time graph, and I think we can use it to think about which of these statements would be correct. So B said that the back reaction rate is at its lowest value once equilibrium has been established. Now that's wrong, because the back reaction actually will be at its highest value for rate at equilibrium, because it starts at 0. The forward reaction rate increases as the system approaches equilibrium. No, not at all. It should decrease. So the answer must be the last one. The forward reaction rate decreases as the system approaches equilibrium. So that's question 8. I think I did make it more detailed than you really need in order to answer the question, but it's always a good opportunity to revise the rate and time graph. Moving on to 9. 9 is a quick question. At a particular temperature, the equilibrium constant for the following reaction is 49. So this Kc is 49. You need to find the equilibrium constant for this reaction, which is at the same temperature. So you don't need to increase or decrease Kc, the original Kc from 49. Now what happened with this one is that it is the reverse of the original, and you also need to notice the fact that the coefficient is half. So half of the coefficient is half. Let's just write that. Reverse and coefficient is half. So if you reverse a reaction, you need to take the reciprocal, okay, which is going to be that. And if you have the coefficient, you need to take the square root. So we would have 1 over square root of 49, which, let's see what it equals to. So 1 divided by square root of 49. I cannot believe I just did that. Oh my god. Oh, that is so bad. So bad. Okay, 1 divided by 7, 0.14. It is late. I don't know whether you can see the clock. Can you tell what time it is? I don't think so. I think I cropped it out of the screen. Okay, answer is B. Let's move on to 10. Let's see whether we can finish this in one go. Question 10. The diagram below shows the distribution of energies of particles at a particular temperature. You need to work out what happens when the temperature is decreased. Okay, the total kinetic energy of particles will definitely decrease if you decrease the temperature. The area under curve doesn't change because this is total amount of particles. So total amount of particles. Okay, so we know it's not, well, that doesn't help, does it? So we had to look at this proportion of particles with more energy than E. Now, if I draw the graph of the temperature, the graph of the distribution at a lower temperature, it probably is going to look, well, not like that. Okay, let's try again. I don't know, this may not go too well. Okay. Oh, that's terrible. Can I even do this? How about if I start from this end? Oh my god. Okay. Alright, I'm gonna leave it at that, I think, because if I try again, it may be even worse. So let's say this is lower temperature. So you have a higher peak, but less particles meeting E. So the proportion of particles with more energy than E should decrease, which means the answer is D. Okay, that should be an easy question, hopefully. And from that easy question, we have 11, which is not an easy question at all. And I'm going to just change the position of the graph so I have a little bit more room to write. Okay. So a lot of things are happening here. At the same time, this graph has appeared quite often, so you do need to make sure that you can interpret them. Temperature and pressure are key factors in the production of common chemicals via equilibrium reactions. The data below shows the relationship between percentage yield product, temperature, so the temperature is actually the different curves, and pressure is the horizontal axis. According to these data, so there are quite a few things. Now you need to look at two different things when you look at this graph. So I'm going to start with temperature so I can determine whether the forward reactions is exothermic or endothermic. So if I just look at the height of the curves, at 700 degree, the percentage yield is lower than at 200 degrees. So the 200 degree curves has a percentage yield of almost 100%. When it goes down to 70, it's only around 10% or maybe 15%. So what it's saying here is if you increase temperature, according to the graph, increased temperature will decrease yield. Now what this implies is that when you increase temperature, you have a lower K value and less product, which means that you have more back reaction. You will have a lower K value and less product when there is more back reaction than forward reaction. So ultimately what it means is that the back direction must be endothermic, because when you increase the temperature, the system will always go towards the endothermic side. So the back is endo, which means that the forward is exo. Okay, so that's from the temperature. So I can cross out A and D. The second thing that we're going to look at is the pressure. As you increase the pressure, so let's say when the pressure goes from 200 kilopascal to 400, the percentage yield increases. So when I increase pressure, that will increase yield. As you can tell that this point has a higher Y value than that point, so the percentage yield is higher at 400 kilopascal. Now if you have a higher yield, then it means that the system is going forward more, because higher yield mean you have more product. Now K is not going to change here because you haven't changed temperature. The temperature is still at 700 according to this curve, but the pressure changes. That doesn't change K. So I just have more product, and if I increase pressure, the change is always going to be going to the side with less mole, because increasing pressure will increase concentrations of everything, and the response for that is to go to the side with less mole, and that means that the side with less mole is the forward, because the system goes forward as indicated by higher yield. All right, so the product must be on the side with fewer particles. Answer is A. So that's 11. Now this is a difficult question, but I really recommend everyone to make sure that you understand what's going on. And this type of graphs can come up again and again. So it's very, very important to understand the relationship between yield and equilibrium behaviors and temperature and pressure. Moving on to 12. The catalyzed reactions of benzene with chlorine is exothermic and occur in a two-step reactions process. The first step is endothermic, so the whole thing is exo, and I have bolded this. The first step is endothermic and has a high activation energy. It produces an intermediate known as carbocation. Okay, if the first step is endothermic and it also has a high activation energy, anything that's endothermic must have the enthalpy of the product being higher than that of the reactant, and this is what I'm going to use to indicate a high activation energy. And the carbocation is the intermediate. The reaction of this carbocation in the second exothermic step. So the second step is exothermic with a lower activation energy. So a low activation energy and is exothermic. And also the whole thing is exothermic, which means that the final product must have a lower delta H than the original reactant. So it should look like that. Okay, I think that's B. Question 13. Considering the reaction shown in the following equation, you're given an equilibrium system and you're given the K value. If you have this, Okay, 10 ml of NOBr, 10 ml of NO, and 5 ml, I think I just said mole of Br2 are placed in a 1.0 liter container. You need to predict the direction that the reaction will proceed. Now, this is a classic K versus Q question. So you have a reaction mixture, but you don't know whether it is at equilibrium or not. So you're going to have to work out Q. And fortunately, the volume in this case is 1, so you don't have to do any complicated conversion or calculations. The number of mole will be identical to the concentration. So to calculate Q, I need to use the same formula that I would use for K. So it will be NOBr square over NO square and BR2. Okay, and that is going to be, so NOBr2 is 10 square over 10 square times 5, which is about a fifth. Okay, and now you need to you need to compare this number with K. So it is 0.2, which is less than 1.3. Actually, no, 0.2 is greater than 1.3 times 10 to the negative 2. I almost did not see that. So if you're not sure, you can always use a calculator to convert all of this into decimals. It's better to be safe and look ridiculous in the proof. No one will know. No one will know. It's a multiple choice question. So because Q is greater than K, it means that when the system wants to eventually reach equilibrium, and it is going to do that by trying to reduce this Q, which means that it needs to move backwards. So it could actually reduce the amount of product and increase the amount of reactants. So the reaction will shift backwards to reach equilibrium. It's C. Almost finished. We have 2 questions left, 14 and 15. The decomposition of phosphorus pentachloride can be represented by the following equation. A quantity of PCl5 is placed in an evacuated vessel and allowed to reach equilibrium. The results obtained during one experiment are shown on the graph. And then you have a range of variables which may have been measured during the experiment. And you need to see which one will match the graph. Okay, let's go through of them. First of all, rate of the forward reaction. Now, the rate of the forward reaction is not going to increase over time. The rate of the forward reaction should decrease over time. And this graph had the rate is increasing over time, so you cannot measure the rate and get this graph. Second one, concentration of PCl3. Potentially, because you start with PCl5, so over time the concentration of PCl3 is going to start at 0 and it's gonna increase over time. So you can potentially measure the concentration of PCl3 and get this graph. Now 3 is an interesting one. Total gas pressure in the vessel. It's very unlikely that the total gas pressure starts at 0. Does not start at 0, because you always need you start with some gas, and also even if you assume that that value is not 0, the gas pressure should probably double because you're producing twice the amount of mole or particles compared to the reactants, but that's clearly more than double, so that's not going to be 3. So this one does not start. Let me just finish that at 0. Okay, so it's not 3. Always keep in mind that questions that have to do with gases can always come up because it's something that you've learned. And the last one, gas pressure of Cl2. Now that is going to increase over time as well, very similar to concentration of PCl3, because you start at 0 and then it should increase until it reaches equilibrium. So I think the answer in this case is going to be 2 and 4. Okay, last question. Which of the following will increase the equilibrium concentrations of PCl3? Okay, increase concentration, equilibrium concentration. Let me just rewrite the equation so I don't have to keep going back and forth. I think they're all gases, so this go to PCl3 and Cl2. Okay, we want to increase equilibrium concentration of PCl3, so we want for more forward reaction or something. Decrease the volume of the vessel. Now, if I decrease the volume of the pressure of the vessel, that's the same as increasing concentration, and the response is going to move not forward but backwards to the side with less particles. B, increase the total gas pressure by adding nitrogen gas to the equilibrium mixture. Now, this is not going to do anything to the equilibrium system because the system doesn't respond to the addition of an inert gas. So PaCO3 is not going to change in concentration after this happens. If I removing chlorine gas from the equilibrium mixture, now that's good because this is going to cause more forward reaction, and you're definitely going to have more PCl3 being produced. You will have more forward reaction because you remove a product, so the system wants to replace that. Using a catalyst does not affect equilibrium, so the answer has to be C. Let's just quickly write this down. This does not affect equilibrium. Okay, so answer C. And that's it for the multiple choice section.